Okay, so today we're heading into the last chapter, chapter 6, which is really about something called diagonalization. Okay, right. So you have some linear transformation. You have some matrix, and you're trying to find a basis with respect to which that thing is diagonalized. Okay, so we'll have sort of different versions of this, and it's not always possible. Okay, so there's no guarantee that you'll get diagonalized. If you go on and take a second course in linear algebra, there is like an advanced linear algebra course. I think it's 173 or something like that. Then you'll see these things called like the Jordan canonical form or something like that, which is basically some way of getting as close as possible to diagonalized. Okay, and that's actually useful in differential equations and stuff. But we're not gonna get there. Okay, so 6.1 is our first steps in that direction: eigenvectors and eigenvalues. And so these are things that we've mentioned sort of like from time to time. We've seen them occasionally in the course. You start off with a matrix, right? You start off with a matrix, and let me say it this way: if there exists a vector, if there exists a vector v, a non-zero vector, so if there exists a non-zero vector v such that AV equals lambda v for some complex number lambda, okay, then we say that lambda is an eigenvalue of A. And we also say that V is an eigenvector sort of belonging to lambda. Eigenvector of A belonging to lambda, or just with eigen, maybe it's, nobody says that. An eigenvector of A with eigenvalue lambda. Okay. Another term that will be important is something called an eigenspace. So if lambda is an eigenvalue of A, then we let E sub lambda denote all vectors in Rn such that AV equals lambda V. Okay, so that's all the eigenvectors with eigenvalue lambda, and I often just abbreviate it as E vector or eval. So that's eigenvector and eigenvalue. Okay. Okay, so that it's just all the eigenvectors with eigenvalue lambda, but it also includes 0. Okay. So plus the 0 vector. Yeah.
So is the 0 vector an eigenvector?
No. No. So only non-zero vectors are eigenvectors. But in this space here, we do throw in 0. Okay, and this thing is called the eigenspace. I'll just call it an eigenspace. Okay, so, right, nothing too fancy, right? Matrix, vector, matrix and vector. Normally, when you hit a vector with a matrix, it it doesn't just stretch, but it like moves. It changes its angle or something like that. But here, we've got some special vectors. You hit them, and then they just get scaled by a scalar. Okay, it's a complex scalar, so maybe not so simple, but in any case, it just gets scaled, right? And the scaling factor is called the eigenvalue. The thing that gets scaled is the eigenvector. The collection of all the eigenvectors plus 0 is the eigenspace. Okay, so nothing too complicated. Maybe I'll have you guys think about this as an exercise. Each of these things is actually a subspace. So claim any eigenspace is actually a subspace. Okay, so see if you can figure, take a minute or two and think about it and see why that's true. Okay, so I'll go walk around outside.
Makes sense, because when you scale the vector, you can scale more. But it's the added one and stuff. So these subspaces are added. Well, sometimes you can add two eigenvectors, and then move it from the scalar. Same thing as scaling.
Okay, talk to a neighbor, please. Talk to a neighbor.
Yeah, I'm going to check. Or does it have to be an eigenvector of the eigenvectors?
Okay, anybody want to try? Like, how can we show that this thing is a subspace? Right, this is right, eigenspace, remember, it's everything such that AB equals lambda V. Right? So why should that be a subspace? Yeah, Izzy.
Well, so in terms of, because the subspace has to work with addition and scalar multiplication.
Okay, yeah, so we want to show, so one way is to, let's show that this thing is closed under scalar multiplication and vector addition. Right? Yeah.
So we figure out the scalar one. If you just multiply
Sure.
that
So-
vector v by any scalar, like alpha or something, when you put the matrix to it, if it's scaling it, the matrix will scale it, and so will the scalar. So it just is still, it's still closed.
Exactly. So you say, well, suppose this guy is in the set, and you want to show that any scaling of it is still in the set. Right. Right. Well, to show that this guy is in there, we have to show that it satisfies the property. Right. So let's check that. Well, A times alpha V is just going to be, well, you can always pull the scalar through the matrix, right? So you can pull the scalar out, and you just get alpha AV, right? But alpha AV is just alpha lambda V, right? But that's lambda alpha V. And you can put the scalar back in. You can pass the scalar back through the other scalar, right? And so you get lambda times alpha V. So that means that A of alpha V is lambda alpha, is just the stretching of alpha V. Right? So that's good. Okay, so now we need to show closure under addition. So say that U and V are in in the eigenspace, okay, we want to show that the sum is in the eigenspace, right? So again, we say, well, well, let's take A of the sum, right? What happens? You can pass it through, right? Right? This is a linear transformation, right? So you can, this is just going to be AU plus AB, right? But these are eigenvectors. Each of them is eigenvectors. Is an eigenvector, so we get lambda U plus lambda V. Distribute out. You can always distribute. You get lambda of the sum, right? And so A times the sum equals is just the stretched sum. Okay. 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 So that's one proof. Let me show you a slightly more fun one. So you say, well, look, V is in the eigenspace. It's the same thing as saying that AB equals V. I'm sorry, AB equals lambda V, right? Which I'm going to rewrite as AB equals lambda times the identity matrix times V. Okay. Be impressed. No, don't be impressed. Right. Multiplied by 1. Okay. Now I'm just going to subtract on both sides. I'm going to distribute. Right. So I get A minus lambda I V equals 0. The 0 vector. Right. Right. So subtract, move this guy to the other side, and then I distribute out. Right. But that means that V is in the null space of A minus lambda I. Right? Well, the null space is a subspace. We know that, right? Null space is a subspace. So you know, being in here, what you see is that E sum, the eigenspace is simply the null space of A minus lambda I, right? Which is a subspace. Okay. Okay. Any questions? Okay. Let me give you another one, another exercise. So, exercise 2. Lambda is an eigenvalue of A if and only if the determinant of A minus lambda I is 0. Okay, so think about that for a minute, please. Yeah, Emma.
Actually, a question, why
Yes.
are we multiplying by I at all? Like,
Well,
can we not move
I can't-
it otherwise?
I can't talk about the determinant of A minus a number, right? Like I could have pulled this, right? If I said here, like, yeah, this is like, suppose I do it this way. So that's the same thing as saying that AB minus lambda V is equal to 0, right? But now I can't, you know, maybe I can, so it's okay, I can factor out like this. But now it's a matrix minus a number times the vector equals 0, right? And I can't talk about the null space of a matrix minus a number.
So you're just turning lambda into a matrix.
Yeah.
So
Yeah.
you can't use.
Yeah, so instead, you know, because multiplying by lambda is the same thing as multiplying by this matrix, right? 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 That's the same thing, so
Yeah.
just just to make it a matrix.
Makes sense.
Okay, so yeah, think and talk. I'll be back again. I'm just gonna.
You said null space is the whole space. So then what it would have to be.
Oh, right, so then you have with 0. I'm kind of catching your drift.
Because what is the null again?
What is the dimension of the null space?
So if the null space is the entire space, then by the way here that would have to be 0. Because that is insane.
The rank?
Right, because isn't the null space of
No,
oh
no.
wait, I'm thinking
You're thinking of rank of that.
okay, wait, what's the I feel like that's not
Okay, you should be done already.
Oh.
Did anyone figure it out? No. Anyone figure it out? No? No, sorry. That was rude. Okay, look, let's think. So this guy is an eigenvalue. Should I go back outside? No, I'm gonna stay here. Okay. So this guy's an this is an eigenvalue if and only if, right, AB equals lambda B has a solution. Right? Right? In other words, there's got to be somebody, has a non-zero solution, so non-trivial solution. Okay. Again, that's the same thing as saying that the null space of oops, A minus lambda I is not the zero vector. Right? There's more than just the zero vector in here. In other words, Izzy.
Is it by like the
Exactly.
characterization of invertibility that
Exactly.
it's like if the null space
Exactly.
is trivial, then it's like works, so the opposite is true here?
Yeah. Right. So right, the only way, if there's a non-trivial solution to this, that means that this is non-invertible. Right? That means that the determinant is 0. Right? So we just use the characterization. Right? So this is the same thing as saying that the determinant of that means that this is not non-invertible, but we know what that means, that the determinant must be 0. Right. So yeah. So this was basically like, do you remember that the old theorem about characterizing invertibility? Okay. Okay. So this is everybody okay with that? So this is actually a useful tool. It says that if we want to find the eigenvalues, then we look at the determinant of something like this. Okay. So let me show you what this means. So let me give you an example. So application. Okay. So let's suppose that the matrix A is a 2 by 2, 6 minus 4, 3, negative 1. Okay. We know that lambda is an eigenvalue of A if and only if the determinant of A minus lambda I is 0. So 6 minus lambda minus 4, 3, negative 1 minus lambda. right, by what we just said, to find the eigenvalues means that we want to find the lambda for which this thing equals 0, right? Right. I'll probably mess this part up. So this is, what's the determinant here? It's this minus, minus that, right? And so we get lambda squared, we get a plus a lambda, minus 6 lambda, so we get minus 5 lambda, and then we have a minus 6 plus 12, so it's plus 6. Okay. Right. So that's, if you factorize it, right, you get lambda minus 2 times lambda minus 3. Right? So what are the eigenvalues of A? It's 2 and 3, right? Right? 2 and 3 are the eigenvalues. Okay, so it gives you this cool way of finding the eigenvalues, right? That's not something you would just figure out, you realize just from the beginning, right? Like, oh yeah, just create this polynomial, and then the roots of the polynomial are the eigenvalues. But it's actually pretty straightforward, right? If you understand the characterization of invertibility, this is you would come up with this pretty quickly. Yeah.
Are those eigenvalues specific to like the eigenvectors? Oh wait, but A isn't an eigenvector.
There are no eigenvectors yet. All we know are eigenvalues. This is the cool thing. We don't have any eigenvectors. We just using this trick here, we pulled out the eigenvalues without any eigenvectors.
But from that, could you figure out what the eigenvectors are?
Then we can figure out the eigenvectors from there. Yeah, exactly. So we use this because we say, okay, now let's just look at the null space of A minus 2i and A minus 3i, right?
Mm-hmm.
So that goes back to what we did at the beginning, just like finding the solution to the homogeneous problem for a matrix. Matrix X equals 0, right? So finding the null space. Okay, so all that stuff we were doing at the beginning, which was so calculational, actually comes into play here. Okay, let me put some names down. So definition. This determinant of A minus lambda I is called the characteristic polynomial. Oops, polynomial. Okay, and what we've just seen is that the roots of the characteristic polynomial are the eigenvalues of A. So now, once you found the eigenvalues, then we can use this. So finding the eigenspaces. As we just said, A sub lambda is the null space of A minus lambda I, right? So if we want E sub 2, right? If we want E sub 2, we just calculate the null space for A minus 2. So look at the null space of A minus 2. That's going to be 4, negative 4, 3, negative 3. Right, so A minus 2. Right? And you see that by Gaussian reduction, that reduces to 1, negative 1, 0, 0. Right? Just looking at it, you can see that it reduces to 1, negative 1, 0, 0. And so you see that the null space is just the things where x and y are the same, right? So E2 is going to be everything of the form, is going to be the span of 1, 1. Right? Everybody okay with that? This may be kind of too old. You may have, this may be rusty, but we've seen this. Right? And then same thing, E3. Right? We want the null space of, we're going to look at that guy minus 3. Right? So we get 3, -4, 3, -4. Which is the same thing as 1, -4/3, 0, 0. Right? So the first guy is going to have to be 4/3 of the second guy. So you have 4/3, 1. So E3 is this span. Yeah.
So if this is the whole space for the one eigenvector, like at some point you said it was like the list of each vector that works with the eigenvector, or the eigenvalue?
Yeah.
Does that just mean that that's gonna be the eigenvector, because it's what works with the,
Well, the whole, that span is, there's infinite number of eigenvectors,
Okay.
right? There's, any multiple of this
Gotcha.
is gonna be in E2,
Okay.
right? So E2 is a whole line, right?
gotcha.
It's gonna be 1, 1. This is E2 right here.
Okay, that makes more
Right?
sense.
And then 1/4, 1/4 is the other one,
Okay,
right?
that makes sense.
Okay. Okay, let's see. Let me put up some exercises for you to try. Let's see. Okay, so here's some exercises. One, suppose A squared, so A is a square matrix, and A is the same thing as A. Okay, so when you square it, it just gets back to itself. Okay, so claim the eigenvalues must be 0 or 1. This term, this kind of matrix has a name. It's called idempotent. We don't use this word very often, but it does have a word. Okay. Okay, and number 9, suppose that a to the k equals 0. Show that all eigenvalues must be 0. The only eigenvalues this guy has is 0. And these kind of matrices also have a name, nilpotent. Take a minute or two and see if you can get somewhere on this. the problems are pretty similar. If you can get one, you can get the other. So just do one of them. Okay, talk with the neighbor for a minute, please.
So I did the first one. Did this, split both sides by b. And then I was like, oh, well, this one's lambda b. But I was like, oh, but if this is a times something, the something's gonna have to be the same. So this times itself would make that 1, but if this was 0, b is also 0. So 0 or 1. Because it was a times a. You're good.
Wait, why is 0?
It's just cause.
No, like 1 makes sense. But that sounds right the word
Just cause. But that would make. Yeah. Yeah, that makes sense. That 0 squared is looks like 1 if it's the 1, but 2 squared is not 4. That's too much.
Okay, so let me try and lead you guys through it. So you say, okay, look, we're trying to say something about the eigenvalues, right? So let's say that lambda is an eigenvalue, right? That means that so AV equals lambda v for some v, right? That's got to happen, right? If this is an eigenvalue, it must have some eigenvector, right? Okay, so we know AV equals lambda v, right? There's some vector AV equals lambda v. We also have this other fact, right? That a squared equals a, right? A squared equals a. Well, how we got to bring that in somehow, right? Right. So what should we do? It's obvious. Multiply this thing by a, right? So let's multiply that by a, right? Because we have this fact. We should use it. Right? We know that. So multiplying both sides by a, we get this. Oops. Right. Right, or is that the right thing to do? I'm not sure. Does that help us? Yeah, it helps us, right? Because, so what do we get over here? What happens here? We get lambda AV, right? Well, lambda AV is going to be lambda, AV is going to be lambda V, right? What about AAV? What's that? That's AV, right? That's just AV, right? So AV equals lambda V, but also AV equals lambda squared V, right? So that tells you that lambda equals lambda squared, right? This V is non-zero, remember. V was non-zero. So lambda equals lambda squared. Well, that means that that lambda must satisfy lambda squared minus lambda equals 0, right? In other words, lambda is a root of this polynomial, and so it must be 0 or 1. Okay. Okay, so I hope doing these sorts of things is getting easier with time. I hope you see, you just have to use your knowledge, right? So we're thinking about eigenvalues. What does it mean to be an eigenvalue? It means that this sort of thing is going to happen, right? And then you have to use the facts that you're given, right? You have to bring them in somehow, and then see what happens, right? And then see what happens, and then the right thing happens. Okay. Okay, I'm not sure if I'm going to make it do everything I want to do, but let's see. Okay. 10 minutes, 13 minutes. Which one should I do? Okay, let's go for the hard one, and if we have time, we'll get the easy ones. 15 minutes is definitely enough time to do the hard one. Okay, so so I was going to start off with some simple observations about eigenvalues, but I'm going to instead start off with the complicated one. So, not so simple observations about eigenvalues. Okay, so let's go back for a second and think about this matrix. 6, -4, 3, -1, right? And it had eigenvalues 2 and 3. Okay. Now, what's the determinant of this matrix? -6 minus 12, that's 6, right? I don't remember if you encountered this term in your homework yet. Trace. You guys seen trace? What's trace? Do you remember? You just sum down the diagonal. Okay. Sum down the diagonal, you get 5 here. Okay. Now, what do you? Anybody see a relation between 2 and 3? Like 2 and 3 and 6 and 5? Well, 2 times 3 is 6. 2 plus 3 is 5. Right? So that is basically, if you had a matrix with these guys down the diagonal, then the determinant of it is actually the same as the determinant of the original matrix, right? The trace is actually the same as the trace of the original matrix. Okay, that's not a coincidence. That's what always happens. Okay, and so that's the theorem that we're going to show right now. That if you have an n by n matrix and p of lambda is the characteristic polynomial, okay, and lambda 1 through lambda n are the roots of that polynomial. Some possibly duplicated. Okay. These are, of course, the eigenvalues, right? As we mentioned before, these are the eigenvalues of A with duplication. Then the product of the lambda I is actually the determinant of A. I think we've used this notation before, the product, right? The product of the lambda I is the determinant of A. The sum of the lambda I is the trace of A. Okay. Okay, yes?
So if a matrix only has one eigenvalue, then would that eigenvalue be the determinant?
Well, if it's an n by n matrix and it has one eigenvalue, then that means that it has a multiple, it has n copies of that one eigenvalue.
Oh, okay.
Yeah, there's going to be n roots because the characteristic polynomial is degree n, right? You have a polynomial of degree n, it has n roots, some possibly multiples, right? And so if there's just one value, there must be n of that one value. Okay, so before we do it, we're going to do something kind of trivial. So suppose I give you this polynomial. Let me make it a bit smaller. Okay, suppose I give you this polynomial. Okay, and I say, what are the right? This is something x to the fourth plus something x cubed plus something x squared plus something x to the 1 plus something plus some constants, right? Right? And I say, give me the coefficients of this, right? One way of doing it would be to multiply it all out. Okay, that will certainly work. But there's a more clever way of doing it, which is to say, how can I get x to the fourth? Right? And you say, oh, well, if I'm multiplying all these things together, the only way I can get x to the fourth is this times this times this times this. Right? There's no other way for me to get x to the fourth. Right? If I take a different thing here, this times this times this times this, I get something x to the third power. Right? So the only way I can get an x to the fourth power is, there's only one way to do it, right? And that is this times this times this times this, and you see that the coefficient is 1. Right? Because the coefficient is just 1 times 1 times 1 times 1. Okay. Now, how many ways, what's the coefficient of x to the third? Again, you can multiply it out, but it's better to do it this way. And you say, well, I could take this -3 times this times this times this, right? I could take the -2 times this guy times this guy times this guy. I could take the -5 times, et cetera, right? And so you see that what I'm going to get is just -3 plus -2 plus -5 plus 7, which is -3. Right? That makes sense? Okay, right? How many ways can I get squares? Well, I have to choose two of these guys and 2 of these numbers, and you just see, like how many pairs. I just take all pairs of numbers, multiply them, and then add them all together, and that'll give me these guys, right? How many ways can I get 1 power? Well, I would have. Okay, I hope it's clear enough. Yeah. Okay, clear enough. Okay, so this observation, this kind of funny way but smart way of calculating the coefficients of your polynomial is going to be crucial in the proof, actually. Okay, got 5 minutes. Okay, so I'm going to do it for, I'm just going to show this proof in the case of 3 by 3. So proof in the case of n equals 3. The general proof is exactly the same. Okay, so don't worry. Okay, so first, 1. Note that, the characteristic polynomial is the determinant of a minus lambda I, which is a polynomial of degree 3. Right? Polynomial of degree 3, and so it has 3 roots. Some possibly the same. Okay, so let's call this 3 roots lambda 1, lambda 2, and lambda 3. Okay. Okay, so then that means that P looks like some constant lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda 3. Right? That's what your polynomial is going to look like this, right? It's got roots at lambda 1, lambda 2, and lambda 3, and so it's right. You can factor the polynomial into linear parts. Okay, so part 2. So now let's write, let P of lambda be written as B0 plus B1 lambda plus B2 lambda squared plus B3 lambda cubed. Okay, so I'm just putting notation. So notation, right? Let the coefficients be denoted by b's. Okay, what do you see? Comparing the two things, comparing the two notations, you see that B3 is the same thing as C, right? B3 is the coefficient on lambda cubed. The coefficient on lambda cubed here is C, right? So B3 is C. C is B3, and then for B2, we play that game, right? We're saying how many ways can we get squares? Well, we can get, lambda 1 times lambda times lambda. I'm saying negative lambda 1 times lambda times lambda. We can get negative lambda 2 times lambda. We play the game, right? And we get summation of the negative lambdas times C. Right? Okay. Let me call this fact star 1. Let me call this fact star 2. Okay. Now, part 3, P lambda, remember, is the determinant of our matrix, right? Our matrix A11 minus lambda, A12, A13, A21, A22 minus lambda, A23, A31, A32, A33 minus lambda. Right? Just, that's what it is, right? So let's expand the determinant down the first column, first row, right? So this is going to be A11 minus lambda times the determinant of A22 minus lambda, A23, A32, A33 minus lambda, minus A12 times the determinant of A21, A23, A31, A33 minus lambda, plus A13 times the determinant A21, A22 minus lambda, A31, A32. Okay, so we just expand down the first row. Okay. Okay. So observe. The only term, involving more than one diagonal element, right? If we think about these diagonal guys here, there's only one thing that involves more than one. Right here, there's nothing that involves more than one diagonal term, right? Nothing. The only way you can get more than one diagonal term is this first thing here, right? This guy times this thing, right? Right. So the only term, when we expand this all out, the only term that involves more than one diagonal element is this thing, A11 minus lambda times A22 minus lambda times A33 minus lambda. Right? Right. That's the only thing, when we write this thing out, that's the only thing that has, right? So what does that tell you? The coefficient of lambda cubed in the characteristic polynomial is -1 cubed. right? There's only, here's the characteristic polynomial, right? The only terms that involve more than one lambda are here. Here they are, right? The term that involves lambda 3 times is this one right here. So the coefficient is -1 cubed, right? What about the coefficient for lambda squared? For lambda squared, well, again, we're going to get -1 squared times A33, -1 squared times A11, -1 squared times the last guy, right? So we get -1 squared times summation Aii as I goes from 1 to 3. Okay, so now putting that together, we get that that this thing here, this C must have been -1 cubed, right? So what do we get? C equals -1 cubed, right? So P of lambda equals -1 cubed times lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda 3. Okay. I should probably let you go. I should. Yeah, actually, sorry. We just have like two minutes to do it, but I think we're already over time. So I'll start up with this at the beginning next time. Sorry about that. Thought we could do it. If I just can just show one thing, sorry. So this is, remember, this is the determinant of A minus lambda I, right? So the determinant of A is, let lambda equal 0. What do you get? Lambda equals 0, you get -1 cubed times, right, -1, lambda 1, lambda 2, lambda 3. The negative ones here cancel out with the negative ones, and you just get the product of the lambda I. So the product of the lambda I is the determinant. And then we can see the trace in like 1 minute later. Okay, so we'll do it again. We'll do it again next time. Okay, so I thought I would just record the last part. I wish I had not erased the board. It's really just a minute longer. I don't want to waste so much time on the next class. So, so remember we had a couple of things. One, P of lambda is C lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda 3. We called that star 1. We also had that C of negative lambda I from I equals 1 to 3 was P2, and we call that star 2. And we just showed that in the polynomial, the coefficient of lambda cubed was -1 cubed, and the coefficient of lambda squared is -1 squared summation aii from I equals 1 to 3. Okay, so now we just need to put those things together. Here, right, the coefficient of lambda cubed was -1 cubed. So let's just replace that here. We get a -1 cubed here, right? And like I just said, P of lambda is the determinant of A minus lambda I. So, so P of 0 is the determinant of A. The determinant of A, P of 0 is, negative 1 cubed times negative 1 cubed times the product of the lambdas, right? So we just get the product of the lambdas. Okay. And then for the second part, we say, well, okay, this C, remember, is now negative 1 cubed. So this thing here is the coefficient of lambda squared. But we worked out over here, right, that the coefficient of lambda squared is negative 1 squared times times that thing, right? And so what do you get? Right, we get negative 1 cubed times negative summation lambda I equals 1 cubed equals negative 1 squared summation AII from I equals 1 to n, right? 1 to 3, right? And so you see that, right, the negatives all, there's a negative here, that all cancels out, and we end up with summation of the lambda I equals summation of the AII, right? In other words, the trace of the original matrix equals the trace of a matrix with the eigenvalues down the diagonal. Okay, right. Okay, so yeah, so the trace of A is actually the sum of all the eigenvalues with multiplicity counted. The determinant is the product of the eigenvalues with multiplicity counted. Okay, and then the proof for the general case is identical. Almost basically the same thing. Okay, that's it.